Okay, so in this lecture we will derive Heisenberg's uncertainty principle from the concept of wave packet. So Heisenberg's uncertainty principle from wave packet. Okay, now how to write down a wave packet mathematically? See, suppose psi xt is the wave packet. Now normally we write it as 1 by root over 2 pi integration from minus infinity to plus infinity a, which is a function of k, e to the power I kx minus omega t, and this integration is over k. So see, this is a plane wave and I am performing this integration over k. So k is varying continuously. Now k is related with the wavelength as k equal to 2 pi by lambda. Now as k is varying continuously, that means lambda is also varying continuously. Lambda is the wavelength of the wave. Now that means in this integration we are actually superposing several infinite number of plane waves with continuously varying wavelength, that is lambda, or continuously varying k. So if we superpose an infinite number of plane waves with continuously varying wavelength or wave number k, we get a wave packet. We get a wave packet. Okay. Now to derive Heisenberg's uncertainty principle, we will assume that ak has an appreciable value, a significant value only over a particular range of k. So we assume that ak has appreciable value only in the range delta k, and ak is sharply peaked at k equal to k0 in delta k. So suppose this is the range of delta k, and here suppose I have k0. So ak takes a maximum sharply peaked value at k equal to k0 inside the range delta k. This is our assumption. Now with this assumption I can reduce this integration from minus infinity to plus infinity. I can reduce this integration over the range delta k, because outside that range of delta k this integration will be 0. So I can write down this integration as psi xt equal to integration 1 by root over 2 pi. Now this integration will be in the range delta k, ak e to the power I kx minus omega t dk. So this integration reduces to this, where this integration is over the range delta k, where ak is non-zero. Outside this range, ak vanishes, and in the range delta k, there is a point, there is a value k equal to k0, where ak is sharply peaked, that is, it has a very high value at k equal to k0. Okay, now ak is a complex number in general, so I can write down ak as ak equal to mod of ak with a phase factor e to the power I phi, and that will be a function of k. Okay, so I will write this expression here. So psi xt is equal to 1 by root over 2 pi integration delta k mod ak e to the power. Now I will have phi k, so I phi k plus kx minus omega t. This integration is over k. Okay. Now in general, omega is a function of k. Omega in general is a function of k. Okay. Now I will do Taylor expansion of phi k and omega k around k equal to k0. So perform Taylor series expansion of phi k and omega k around k equal to k0. Okay. Now what will be that expansion? Now phi k will be phi at k0 plus d phi k dk at k equal to k0 into k minus k0 plus d2 phi k dk square at k equal to k0 k minus k0 whole square by 2 factorial plus dot. That is the higher power terms. Similarly, omega k, I can do the Taylor expansion. Omega k0 plus d omega k dk at k equal to k0 k minus k0 plus d2 omega k dk square at k equal to k0 k minus k0 whole square by 2 factorial plus dot. So these are the Taylor expansion of phi k and omega k around k equal to k0. Okay. Now we assume that this k minus k0 is so small that we can neglect the higher order terms. That is, the quadratic and the higher order terms we are neglecting. So assuming that k minus k0 is very small, and in this assumption I can neglect the terms from here, that is quadratic terms, that is k minus k0 whole square by factorial 2. This will be a very small quantity, so I can neglect the quadratic and higher order terms from this infinite series, and also I can neglect the quadratic and higher power terms from this infinite series. So phi k will be approximately equal to phi k0 plus d phi k dk at k equal to k0, k minus k0, and omega k is approximately equal to omega at k0 plus d omega k dk at k equal to k0 into k minus k0. Okay, now phi at k0 I am calling it to be phi 0, omega at k0 I am calling it to be omega 0, and d omega k dk, this is the group velocity, that is Vg, and d phi k dk at k0, this is a constant, I am calling it to be as minus x0. So let phi at k0 is equal to phi 0, omega at k0 is equal to omega 0, d omega k dk at k equal to k0, this is the group velocity Vg, and d phi k dk at k equal to k0, I am calling it to be minus of x0. This is a constant term. I am calling just as minus x0. So now I can put these expressions here by considering this new naming. So therefore psi xt is equal to 1 by root over 2 pi integration delta k mod ak e to the power I. Now in place of phi k I will write phi k0, that is phi 0, plus d phi k dk at k0, that I have called to be minus x0. So I will write down phi 0 minus x0. So phi 0 minus x0 into k minus k0 then plus kx minus omega t. Now omega has this expression, so minus omega k0, that I have called as omega 0. So omega 0 t minus this this is Vg, so minus Vgt bracket close and integration is over dk. Okay, now I will insert one term that is called k0x. I will add and subtract. So 1 by root over 2 pi integration delta k mod of ak e to the power I phi 0. Now kx, this term I am writing here plus kx, then I am just subtracting one term, that is k0x plus k0x, so that they cancel. I am subtracting and adding. Then phi 0 I have written, kx I have written, so I will write this term minus x0 k minus k0, then minus omega 0 t minus Vg into t bracket close, and this integration is over dk. Okay, now I will take the terms which are independent of k outside the integral sign. So this is equal to, see, this is independent of k, so e to the power I bracket phi 0, this I am taking. Then I will take minus k0x. No, I will not take minus k0x. I will take plus k0x. So plus k0x. Then I will take minus omega 0 t. Minus omega 0 t. So these are independent of k. So I have taken them outside the integral. So divided by root over 2 pi integration mod ak e to the power I bracket. Now see, I can combine these two terms. So I will have k minus k0 x. So I have written these two terms. So I am left with this term and this term. So minus x0. See, one thing, with Vg I have k minus k0. There is a mistake. So with Vg I will have k minus k0 into t bracket close then dk. There was a mistake. That is, with Vg I have k minus k0. So now minus x0 k minus k0 minus Vg k minus k0 into t bracket close integration over dk. Okay. Now I will, this is over the range delta k. Now I will write it in a more compact form. So psi xt is equal to e to the power I bracket phi 0 plus k0x minus omega 0 t divided by root over pi integration over delta k mod ak e to the power. Now I can take k minus k0 as common. So I bracket k minus k0 I am taking common. So inside bracket I will have x minus x0 minus vgt minus vg into t. So bracket close. This is the integration over dk. Okay. Now at time t equal to 0, psi x0 will have this expression psi x0 is equal to t is 0, so I have e to the power I phi 0 plus k0x divided by root over 2 pi integration over delta k mod ak e to the power I k minus k0 into x minus x0. This integration is over k. So this term is 0 at time t equal to 0. Okay. Now I am calling k minus k0 as, let k minus k0 is equal to delta k, or I am calling it to be, suppose, this delta k, and x minus x0 as, suppose, delta x. So I can write this as psi x0 equal to e to the power I phi 0 plus k0x by root over 2 pi integration over delta k. Okay. Now this is mod ak e to the power I delta k delta x dk.